Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Jia-Yu Ou with us today. Hey, Jia-Yu.
Hi everyone.
Jia-Yu, where are you located at?
I'm in Taiwan National Central University.
Cool. Very good. Let's see. It is April 25th, 2023 as we record this. And is spring in the air in Taiwan?
Not really.
Yeah. Okay. Okay. Very good. And Jia-Yu, what do you like to do for research?
I research majoring on the Mira variable stars
Hmm.
and get the distance with the galaxy. Use
Cool.
the peer relation.
Hmm. Very nice. And that is going to bring us to this very lovely AJ article. It's open access, people. You can go get a copy free in the open access era. A distance measurement to M33 using optical photometry of Mira variables. And Jia-Yu, take us away.
Yeah, that's my topic. Just quick say. And this this paper is a small application with the last year we published. Last year we published the paper with the LNC and SNC, use the regular Mira to get the peer relation.
Yes.
We found the maximum light at the light curve. The dispersion will more smaller than the mean light time. So we use this feature
Yes.
to applicate to this distance the measure the galaxy. So we extend to the N33.
Okay.
Yeah.
Yes, I'm with you.
So this work is also combine the National Central University to and the ZTF team from the Caltech.
Mm-hmm. Mm-hmm.
Yeah.
Yeah.
So we collide the whole 18 years several survey data
Nice. Nice.
combined with the CFHT and the PDF, IPDF, ZTF. Yep.
Yes.
So our candidate is from the Yuan 2018. We select the 1,781 Miras,
Yes.
but we only has the 1,637 target has actual data.
Okay. Okay.
Yep.
Mm-hmm.
So our old data, but in this 1,600 Mira, they have the 428 is unknown type. So we also use the machine learning technology to
Okay.
use the periodic with the color index to do the classify.
Okay. I'm with
Yep.
you. Yes.
So we can move on to the figure one.
Figure one. I'm with you. I get what you're doing here. Okay. Figure one.
Yeah.
And GRB light curves. Here we go.
So yeah, in the figure one, we can see the whole life, whole the Mira life is very, very long years. So in the first is from the CFHT, it's by the Herman 2006. So, so it's the we also have the G-man
Okay.
and the PDF and PDF and the IPDF is from have the R-band
Yes.
and the ZTF also has RIG.
Yeah.
And the pen stop is covered by the R-band and also has the I-band. So we collect the
Oh,
several
yeah.
survey and a very, very long time span scale
Right.
the light curve.
Mm-hmm.
So
Absolutely.
we use this light curve to calculate his periodic with the multi-band long scargo, just like the figure two top figure.
Mm-hmm. Some of our light curve data and figure two.
Yeah.
Let's blow this down a little bit. Okay, figure two. There we go.
Yeah, the figure 2, like of the
Mhm.
first, the top panel, we can see that is from the multi-band long scatter gauge power frequency.
Yes.
So
Okay.
that is a little bit more like a lot of the peak of that. So also we use the multi-band PDN mask to calculate his period, just the middle panel.
Yeah.
So we can see the middle panel, that is the multi-band PDN. Yeah, so
And
we can choose the best periodic just from the list 2 algorithm to calculate his periodic, and also can plot his phase figure. So the blue line just we pick from our sample. So the can see the
oh, got it.
original path is periodic from the 663,
Thereabouts. Yeah.
and now it's the 653.
Okay.
Yeah.
Mm-hmm. Mm-hmm.
Okay, so
Good.
when we get the periodic, so we can move on to the figure 3.
Yes. Okay. With you. Figure 3
Okay.
is a nice wide table and observed properties of Mira's M33. And this is a machine readable table. So you can get the whole table if you want people when you download. Get the whole table. Figure 3.
Yep.
And
So
period comparisons. Okay. Mm-hmm.
yeah, we also combine also to collaboration with our periodic and the UN's 2018 the periodic. We compare that.
Yes.
So it's almost the same.
Very close.
The periodic is calculated almost similar, but the only 4% have a lot difference. So just like the below, the left-hand side is our calculus,
Yes. Uh-huh.
and the right-hand side is the UN's calculus. So it a little bit different, but the face shows our periodic is more better.
Yes. Yes. There is more
Yep.
data there. Definitely. Okay. Very good.
Okay. So
Okay.
and also when we calculate this our periodic, so we can use the like a function to get the mean line magnitude and the maximum like magnitude.
Okay. All right.
Yeah, so we can get each band. And we can
Mhm.
move on to the figure 4.
Yes. Okay. Very good. Figure 4. Phase
The
dispersion.
figure 4 is compared with the difference 4% minus. So we can see in our periodic, the phase dispersion is smaller than use the UN's periodic. So we can see our periodic is more useful to refine the periodic for this 4% minus. And we also do the test
Oh, this is
to, well,
discrepant. Got it. Got it. Okay.
yeah, we also want to do the test with if the whole light curve is masked, almost the 80% dark part. If
Okay.
they mask that, it also can be calculated is right or not right the periodic. We do this test
Okay.
just like the figure 5.
Okay.
So
Let's do that. Figure 5 comparisons. Okay.
yeah, so just like our like of the Herman 26 like of data is
Okay.
more darker, more complete,
Yeah. Yeah.
more complete. So we mask that only the
Only the bright
brighting
parts.
part.
Okay.
Yeah.
All right.
So we usually use this brighting part to calculate the period is very it's not very hard, but it need to more data to calculate the correct periodic. But we can hold the dark part. It's very easily to calculate his periodic.
Yeah.
We do this test just for the future world, just like the use the LSST.
Mhm.
It also can get a more distant and more dark light curve. So
Okay.
the SST get more data, so we can extend to the more distant galaxy or something.
Yes.
So this test just for that.
Okay. Okay.
Yep. So we also want to classify these mirrors. So we compare his periodic with his color
Okay.
in infrared and optical. So just like this, so we can see the priority to the J minus KS.
Okay.
They have the clear two group in the carbon rich and arsen rich in the infrared.
Yes. I'm with
But in the H minus K, it's more missing.
Yes, it is.
Missing. It's more missing. And also we
Highly technical.
calculate with obstacle I minus H. It's
Okay.
whole messing up. It's whole messing up. So if we can get only the J and the K and the periodic, we can classify that. But we only have
Okay.
the optical band with the edge. We cannot classify that.
Okay.
Yeah.
Okay.
So we also text with in LNC, so we can move on to figure 7.
Okay. Figure 7. Rich. There we go. There's our JK.
Yeah. The figure 7, the up panel, just like the SD, is from the SSC covers reach and the other restart
Yes.
with the J minus KS.
Yes.
So it also has the clear two group, but it also have a little confused room in the inside.
Okay.
But we can see the answer
Yes.
below is quite different two part in the figure.
Yes.
So that is means it may be not useful to the extend to the another galaxy, but in the local galaxy, there can be some classified with that.
Right. Okay.
Yep. So we not combine LNC to SNC. And MINC3, we only use SN3 because they have some difference in the metallicity.
Yes. Mm-hmm.
Yeah.
Okay.
So we only use this data to be our training data
Okay.
to training our machine learning algorithm.
I'm with you.
And we test the full algorithm to do the classify. It's a
Sure. Okay.
it's a percentage linear algorithm and can nearest neighborhood, the logistic register and the super vector machine.
Okay.
We use the full algorithm to test which algorithm is more better. So we finally test can get the configuration just in the figure 5, in figure 8.
Mm-hmm. Figure
Yeah.
the cool one. So we'll do a
Yeah.
global so we see everything, and then we'll zoom in as need be. Okay.
Yes. So we can use the configuration to get the how good or how bad enough to classify these two. So
Okay.
in in this four algorithm, only the PLA is not great about the 95%
Okay.
accuracy.
Mm-hmm.
But in the KN logical registry and the supervac machine is all good, more than 97%. So
Okay.
it's very, very good to use
Doing
the
well.
this machine learning technology to classify that.
Yes.
So finally, we pick the KNN algorithm
Okay.
to
Of the
do
choice.
our model.
Okay. All right.
So we use the KNN and the K neighbor number is 15. It means we can get a position and vote the 15
Yeah.
around the data to vote this is the oxygen or carbon. Oxygen and
Yes.
carbon.
Yes.
Yeah. So
Cool.
when we use this training model and we can get a result in the figure 9.
Okay. So we are trained. We are gonna do some classifying. All righty.
Yep. So we do the classified result just like we can see the down below is the oxygen rich and the up below is the upper is carbon rich.
Mhm.
And in final we have the 310 is oxygen rich. Only 34 target is the carbon rich.
Okay. Yeah. Uh-huh.
Yeah. So
Yeah.
in this part, so we can classify this unknown type Mira. When we classify that, we can move on to measure the distance. So
Yeah.
we use the we use the cryogenics model to fix our Likert function. Yep.
Yeah. Yes.
So this is
Yeah.
the same. This is the same function as like the our last published paper.
Right.
So we use this
Mm-hmm.
and we use the LNC distance measure is from the 18.79 and
yes.
we
Mm-hmm.
use
87A. Yeah.
the
Mhm.
yep.
Okay.
So we use distance and use the maximum light to calculate N33. The distance measure is 24.67
Okay.
magnitude.
All
So
right.
yep. So this is
Hmm.
this is first use it's the first time use the Mira and use the maximum light time to calculate the distance measure. So this is the first paper.
Very good.
So we can
Congratulations.
see, yeah, we can see this is just refitting in
Yeah.
the
Residual. Mm-hmm.
I band maxima and I minima, minima, min
Mm-hmm.
magnitude. And the parameter is on the figure. And also we can move on to the final figure is figure 11. So this is
Uh-huh.
we use the LNCs after
Discover.
reach the Likert to get our distance
Ooh.
measure to calculate the 24.67 magnitude.
Mm-hmm.
So we compare to the past paper.
Very
So we
good.
can see our work is just middle in the whole.
Right in the middle.
Yeah, it's very
Okay.
middle is whole in the
Mm-hmm. Here's this
previous
work.
lecture.
Yes.
Yeah,
Can't do a row. Okay. This work right in here
yeah,
in the middle. 24.67.
yeah. It's very so. we use the maximum light curve to get the dispersion, and we prove that it's useful. It can be doing.
Definitely.
So it's new technology or new math to calculate. Don't need to measure the mean light curve. You
Oh,
only need to know his maximum light,
cool.
and the calculator is periodic. You only use the maximum light, periodic, you can get the distance.
Very cool.
It's very it's very useful in the LSST
If you don't have
or the
to
future
definitely.
or the future test goal survey.
Right.
Yeah.
Right.
So yeah, that's is whole my paperwork.
Very good. Jia-Yu, thank you so much for walking us through your very lovely article.
Yeah.
Great. Very good. I got it. Using photometry to get a distance. Very good. Okay. Thank you. And where you mentioned a little bit there at the end. So let me just follow up with that a little bit. Where do you think we go over the next couple of years? Is there going to be more data on M33 so we can fill that out? Are you going to try the technique on other local group galaxies? Things along those lines? Where does it go?
Yeah, it maybe extend to the more galactic or more for longer or
Yeah, because we're
to
already
the
18 years or something. Yeah.
yeah. But also can maybe the open cluster or
Ooh, okay.
some just some more not so longer, just nearly. It also extending because it also can easily to observe the whole light curve.
Correct. Yes.
Yeah. So we can just use maybe maximum light and periodic to get the distance.
Yeah.
It's a new method, so we want to extend to in
So let's
to want to do the more model.
apply it to many. Very good.
Yeah.
Very good. Very nice. Jia-Yu, thank you so much for walking us through your very lovely article.
Okay.
And that will do, everyone. And we will see you on the next one. And hope this made your astronomy day just a little bit better. Bye-bye.
Bye.